Hey everyone and welcome back to my channel. So today we will solve the homework problems that I gave you in the previous lecture of diode circuits. That is the most important questions from diode circuits that can come in your interviews as well as in your written test. Okay, so in the previous lecture I did a few calculation mistakes. I will talk about those here and I will solve the homework questions. But before that I want to make a big announcement that we have started the All India Mock Test 2 for analog VLSI placements, and even if you are preparing for GATE, I will recommend you at least give it because it is totally free, right? There is no examination fees, no registration fees, totally free. Just go to our website prefusion.in and register there, and the examination will be conducted on 11th of August. It will be live. Okay, the test window will be open from 7 p.m. to 11:59 p.m. that is on Sunday, and duration will be of 100 minutes and it will be placement oriented, but I will recommend you to give why, because the technical section will be from analog and aptitude will also be there. Okay, and analog questions will also be like, if you try to solve that examination, right, you will be able to understand your level on analog, how good are you in analog, because obviously it will be a bit difficult from GATE point of view, but still if you perform really well, or if you even perform half, even get 50% of the questions right, you will be very confident with yourself about analog subject. So I will highly recommend, even if you are from GATE, to sit on the examination that is on Sunday. Okay, so and you will obviously get the detailed video solutions on our other YouTube channel, that is Prefusion. Okay, so I have made a separate video regarding this AMIT2. You can go check out it here, and there I have explained all the details about it. Also, another announcement is that there are multiple playlists that are in my channel. That is, one is the circuit queries, in which you will find this current video, which you will see, and there I have tried to solve most of the questions that can come in your written test. Okay, and I have another playlist that is Analog Electronics Decoded. There I have tried to solve the interview related questions, interview related problems. So you can go and watch those if you want to have a good in-depth knowledge for analog VLSI domain. Okay, and also you can go to our website. There we have launched a lot of new courses. You can go and visit our website. Currently we are running a huge offer, and after that the prices will rise of all our courses. So do avail it now, else the prices will rise, and then again you will say that the prices has risen, how will I buy? So now is a great time to buy the courses, because after this you won't get this type of low price anytime in the next few days, right? Next few months or something, I don't know. So yeah, that was a huge announcement. So before starting this lecture, right, so here basically I will do all these questions. And before starting this, I want to talk about the mistakes that I made in the previous video. So in this place, right, where I was solving this question, the first question itself, I computed the voltage here negative. That was correct. But here, right, I wrote the diode voltage as positive because I directly assumed it as V2 minus V3 and not the other way around. The diode voltage VD2 will be from anode to cathode, that is V3 minus V2. So it will be V3 minus V2 and not V2 minus V3. So because we always compute the diode voltage from anode to cathode. So it was my mistake, and that's why instead of being happy here, I should have been really sad, because my assumption actually went there wrong. Okay, so obviously calculation mistakes can happen even with everyone, and you should also be aware of this. Okay, so here I should be unhappy here that my assumption was wrong. The diode voltage came out to be positive, and whenever the diode voltage does come out to be positive, right, it isn't in off state, it has to be in on state if it is greater than the forward bias voltage, forward drop of the diode. So what will happen is I will turn that diode on, and if I turn that diode on, right, if I turn that diode on, what will happen? All of this will become short circuit, and then if I measure the currents, I will find that all of the direction of currents is from anode to cathode of all of the diodes. I have checked it; it is for all of the diodes. So what will happen is all the diodes should be on. That is the correct condition for all the diodes. So all the diodes will be on, and according to that the currents will be like this. You can pause the video and you can check the computations. I don't want to waste your time here. So that was one of the mistakes, and the next mistake was regarding this one, where I have computed this one a bit wrong, this one, right? So here I was computing the current. I just by mistake, V1 was supposed to be 3.75, and by mistake I wrote this number here, and the calculation got messed up. Okay, so this will be 3.75, V1 will be 3.75 and not 6.25. And if you compute the currents like this, the states of the diode will be still correct, that yes, D1 D1 D2 will be on, and this will be total short circuit, and V1 will be equals to V2, and current direction will be only this only. And then if you compute the currents here, and if you try to add the KCL at this node, KCL is satisfying, then that sanity check is also in check, that you have solved everything correctly. So yeah, that was a bit of calculation mistake from my end. Other than that, everything else remains same. So now let's come back to this lecture. So in this lecture, what we will do, obviously I gave you the homework, right? The sinusoidal response of this RC circuit and this RL circuit. So we already solved it with DC and also with simple resistor. Okay, it will be simple resistor divider if we have sinusoidal input. But with RC and RL, right, things will be very, very interesting. So do please listen to me very carefully, and electrical people can relate with this because they study these kind of stuff in power electronics as well. But this will be a very, very good discussion, so you should listen to me very, very carefully here. So there will be bit of AC transient involved here. So let's first solve with the capacitor. So let's first try to understand intuitively what will happen. So obviously capacitor doesn't have any charge initially. So at t equals to 0 plus, how will the circuit be replaced with? So circuit, if I draw it, right, what will happen? Capacitor doesn't have any initial charge. Okay, capacitor doesn't have any initial charge, so the voltage across it will be 0, and I will assume this as a ground point, ground node. So here, right, just t equal to 0 plus, what will happen? This voltage will be somewhat greater than 0. Okay, and the current is almost 0. Before this current is 0, right? Diode is off, current is 0. So this positive voltage come across this, and this is 0. So diode will be on. But the problem here is diode has a cutting voltage. Right? Diode has a forward drop voltage of 0.7 volts. So diode cannot turn on if the VAK is less than 0.7 volts. It has to be more than 0.7 volts. So diode won't be turned on. So what will happen is, if diode doesn't turn on, no current flows. So what will be the voltage across the diode? What will be the voltage? So the voltage V, right? Voltage V. VD will be simply Vs, right? VD will be simply Vs because diode hasn't turned on and this current is 0. So if you just simply apply KVL, you will find VD equals to Vs. Now what will happen is, my VD has to be greater than 0.7 volts for diode to be on, D on, right? So my Vm sine, I will say some angle, omega t it is. So omega I am not writing, they have given us a frequency. I will talk about frequency just in a bit, just hold on a bit. Okay, some angle sine alpha, the value becomes 0.7. Okay, so at this angle alpha, right, what will happen? The VD will be just equals to 0.7. Just after this alpha, VD will be greater than 0.7. So diode will turn on, and if diode turns on, what will happen? The current will flow, and if current flows, right, current flows in this direction, what amount of current will flow? Very small amount of current will flow. Very small amount of current will flow. What will happen is, it will charge the capacitor. Charge the capacitor, right? Charge the capacitor. Okay. Now it will charge the capacitor. What next will happen is, if current is flowing in this direction, because this end potential is more and this end potential is lower. Okay. Current flows from higher potential to lower potential. Now if it is charging the capacitor, the like what is my VC? VC is what is my IC? IC is C dVc by dt. So it is getting inserted in the capacitor. So the voltage will also increase because current is positive. So the voltage will also slowly increase across the capacitor. Now as the voltage keeps on increasing, this will charge. Okay, capacitor will charge. Now until how much it will charge? That is a great discussion. So for that, right, we have to understand, like, there is a AC transient involved here because there is a R and C here, right? So how will the equations look like? So I actually forgot to write the equations. Okay, I need to copy this. This is for this one. So here, right, like this will be the circuit. I'll just, okay, I haven't wrote this for inductor, but this will be followed for capacitor as well. Okay, just hold on, just bear with me a bit. So the current equation, right? So if you haven't studied AC transient already, you have to go out to our channel Prefusion. In the network theory playlist, Himanshu has taught AC transient. So you must check out that video for you to understand this level of this part of concept, right? So when this gets turned on, right, what will happen is this will become a RL circuit with a AC input, and for that you have to study AC transient. So in case of AC transient, right, what happens is this current is some form of this, some sinusoid format and some exponential format. Now this exponential dies down if the here, right, this will be simply, just hold on, this will be T by RC. Sorry for the interruption. Actually, I was computing this angle and this all this magnitude, right, for capacitor, because I have computed this for inductor but haven't for capacitor, because the sinusoid won't dominate much here. Transient response will be more dominating. Why? I will just say, because here if you see, I told you, right, at 0.7 this diode will turn on, current will flow, this capacitor will charge, so capacitor voltage will increase. One thing we have to keep in mind is how will the capacitor discharge. Capacitor is charging like this, right? If I just draw this, let's say capacitor has charged to some 0.1 volts, okay, 0.1 volts. Now how it has to discharge? If it wants to discharge, right, current has to flow from this, like flow from here to here. And is it possible? It will be in the opposite direction of the diode. So it is never possible that capacitor can discharge. So whatever it has charged, right, it will keep that. And whenever the potential across this diode, right, reaches below 0.7 volts, this diode will turn off and there will be no discharging of the capacitor. Capacitor has no discharge path. So here the concept of time constant isn't that important, but it is important for one thing. I will explain that. So capacitor can't get any discharge path. So it will only charge. So if it only charge, right, how much maximum value can it charge to? So what will happen is that, like, this current will only this current will flow, and slowly capacitor voltage will increase. But can it increase greater than this voltage? It can never increase that. What do you mean by that? What is the maximum voltage that I can get at this node? At this node, what is the maximum amount of potential at this node, right? Because this node will always be fixed to 0. The maximum amount of potential that whatever I get here will be the steady state voltage of the capacitor. What is this voltage maximum? It is V maximum, Vm, minus this diode drop, because this diode drop will always be present, right? This diode drop will always be present no matter what. Once this diode, once this 0.7 volt, once this potential across this diode is lower than 0.7 volts, this diode will never conduct and no voltage will pass through. Okay, so what will happen is my Vc maximum and or Vc steady state will be simply 5 minus 0.7, that is 4.3. So we have sorted out the steady state value, that it will be 4.3 volts. And if you observe that, yes, it indeed reaches steady state because current through it is 0 at steady state. So there is no rate of change of voltage. That's why current is 0. So that's why the voltage will settle to 4.3 for this. And here, right, this voltage will settle to 5 because no current will flow. This now this voltage, right, this voltage will keep on fluctuating. Why? Because sometimes this diode gets turned on and sometimes gets turned off. But once it reaches 4.3 volts here, right, once it reaches 4.3 volts, this VD can never turn on. And if this VD never turns on, what will happen is this voltage will be determined this voltage. So our V, right, V will be equals to simply Vs, okay, because there won't be any current flow. So our V, like whatever we have been asked to plot, will be simply equals to Vs. So if in the interview this gets asked, you will say that at steady state what will happen, our voltage V we have been asked to plot, this will be equal to Vs because there will be no current flow at steady state, hence this drop will be 0, this node can come here and this V will be directly equals to by supply. Now but what is happening at transient? So for transient, right, we need to understand about the time constant. What is the time constant whenever this is charging? Whenever the capacitor is charging for initial few cycles, what is the time constant? It is simply R into C. And if you haven't watched my pulse response yet, you have to watch my pulse response video, then only you will be able to understand what I will speak over here. So here time constant is RC. If I just write this in terms of values, it is 10 kilo into 10 micro. So 10k into 10 micro. So it is equals to what? It is 100 milliseconds, right? 100 milliseconds. And what is the time period? Time period is 1 by f. What is the frequency of the given sinusoid? They have told us the frequency is 1 megahertz. So if the frequency is 1 megahertz, it is 1 by 10 raised to power 6. So it is 1 microsecond. What do I observe? Like what is the settling time or what is the 4 tau, where generally if a series RC circuit is present and a DC voltage is given, it settles after 4 tau time. What is the 4 tau? Here, right, 4 tau equals to 400 milliseconds, and our T by 2, because in half time period only it gets the opportunity to charge. It can also get charged in lower cycles, but if you understand carefully, right, it can, like, this is the input supply voltage. After this VM reduces, right, we know at steady state what will happen, it will be somewhere around here, the voltage will be somewhere around here. So it can never charge more than VM minus 0.7, right? So that's why the charging gets finished after this. There is no charging after that. So here, right, that's why I have taken T by 2. This is just approximate thing. So, but if you notice, T by 2 is 0.5 micro. Hence, our settling time is much larger than 0.5 micro. So, it will take huge number of cycles for this capacitor to charge. If you don't understand, you have to go and watch the pulse response video. There you will understand what do I mean by this. So, approximately how many number of cycles does it require? Approximately. I will say this here, cycles, number of cycles. How many cycles does it require? So approximately, right, it needs to get to 4 tau time. It needs 4 tau time, so it needs 400 milliseconds, and in each half cycle it is getting the time to charge, but also not in half cycle, in each quarter cycle, because only this is the period where it is able to charge. Like, I'm just approximating things, yes, oversimplifying it. So this is the period where it gets to charge. Else in this period voltage is reducing from the highest value, so it loses its opportunity to charge as we move along. So this is just approximate. So this is T by 4, right? So this will be T by 4. So this is 1 by 4 micro. So this will be 1000 into 800 into 1000. So this will be almost 8 into 10 to the power 5 cycles. So after 8 into 10 to the power, approximately, this is just approx value, our current, right, our current will look just 0. Our current will be 0 after 8 into 10 to the power 5 cycles. What do you mean by this? So here, right, what is happening? Let's take the first cycle. First cycle, if I just draw this drop, this is the 0.7 volts, right? Let's say this is the 0.7 volts. Now, from 0 to 0.7 in the first cycle, diode doesn't turn on. Okay, just after 0.7, diode turns on because the voltage across the diode is more than 0.7 volts. So what will happen? Voltage is increasing, current flows, capacitor is charging. So what will happen is that the capacitor voltage will also increase. Capacitor voltage will also increase, but the supply is also increasing. So the current is still positive. And after some time, it is still positive. Here, still positive. Let's say our capacitor gets charged to 0.9 volts, like it is charging, and it gets charged to 0.9 volts. Now once it gets charged to 0.9 volts, what will happen? The potential, like if my VC is 0.9 volts, my VD is 0.7, so that node V, right, that node V is simply how much volts? That node V is 1.6 volts, right? And some drop across the R is also happening. So our VS, like it's almost around some, let's say somewhere around here, right? Plus I into R is also happening for us to compute the VS, I into R. So after that, what will happen is, just after this, right, our VS will reduce, but this capacitor voltage is still present. What will happen? The drop across the diode will reduce from 0.7 volts, and if it reduces, diode will turn off. If the diode turns off, the capacitor will, like capacitor was slowly charging, charging, it has stopped here, okay, because diode has turned off. There is no path for the discharge of the capacitor, so it will remain here, and then again in the next cycle it will restart from, let's say, 1.6 volts. It restarts from 1.6 volts, then again it charges, then again let's say the supply voltage reduces, and then again it remains at that, and slowly it charges. Although I have oversimplified, and in 2 cycles you see it has charged so much, but if you observe, the time constant is very high. So for it to charge, right, it will take huge number of time to charge. So that's why it will charge slowly. So approximately it will take around 800 cycles. Okay, so this was just a oversimplified explanation, because this video will go long, very long if I just explain this like over and over again. Okay, so what will happen is, up until this alpha angle is 0.7 volts. Up until this alpha angle, this will be 0. Then slowly it will charge. Let's say to some value. Then again it will remain stable at this. Then again after this 2 pi, right, after again this increasing of voltage has came up, then again it will slowly charge, and this will go on after approximately 8k not 8k, 8 into 10 raised to power 5 cycles. This will go on, and at steady state the voltage will be stable. What is the voltage? It is 4.3 volts. After that, current will be 0 through the circuit, and there will be no drop. And our V, what will be our V? Our V will be simply equals to Vs. So V will be simply equals to Vs. So if they ask you to plot the voltage waveform, V, value of V at steady state, it will be simply equals to Vs, because there won't be any current flow. It will simply equals to Vs. Now let's solve this inductor. This is also very interesting. So again here, right, if I again draw it at t equals to 0 plus, what is happening? At t equals to 0 plus, inductor initially has no current. So if inductor initially has no current, what will happen? And it is in steady state. So if IL of 0 minus is 0, also there is no rate of change of current. So VL of 0 minus will be also 0, because current isn't changing. Okay, current is 0 before t equals to 0. It is always 0, right? So the differentiation of current is simply voltage for inductor, hence it will be also 0, right? So if it is 0, what will happen is, what is the VD? I will assume my VD to be open. If I assume the VD to be open, it will be again, this is 0 volts, right? This is 0 volts, even though it is open circuit, but the voltage is 0. That's the beauty of this thing. Okay, that's the beauty. So this is 0 volts. Now this is grounded, so my VD is simply equals to, this is my VD plus minus my Vs, again at some angle alpha, that is Vm sin alpha, the diode voltage will be equals to 0.7 volts. Again at that voltage, what will happen? This diode will turn on, and what will be the voltage across this? So this current initially is 0, and as the initial inductor current is 0, so it will try to keep it, right? Inductor doesn't want to change its current, so it will try to keep the current 0. And if the current is 0, what will happen? Even though the voltage here is 0.7 volts, the current through this is 0 amps. So what will happen? Solely my VL will be equals to Vs minus 0.7, and I have told you that Vs is just, let's say, just higher than 0.7 volts. So VL will be greater. VL will be greater than 0, and if VL is greater than 0, what do we know? VL is equals to L DIL by dt. Hence DIL by dt is greater than 0. If DIL by dt is greater than 0, that means current is increasing. IL is increasing. Initially current was 0, now it will increase. It will be to some value, right? So as it goes to some value, it will be some value. Okay, let's say it became to, like, I don't know, this is like 10.5 milli, right? So I will say, let's say 10 microamps of current. Okay, it let's say charges to 10 microamps of current. Then what will happen? So I will assume, because it can't, like, I will assume that it hasn't fully charged in the whole cycle. So after that, what at some point what will happen is that this will become negative. So at omega t equals to, I will say at omega t equals to pi, let's say this has charged to 10 microamperes. I'm just assuming things here. Okay, so what will happen? I will draw the circuit at omega t equals to pi plus. Okay, omega t equals to pi plus. So at omega t equals to pi plus, this voltage, right? This voltage will be, let's say, something negative, right? Because sine of pi plus will be something negative. So it will be, let's say, 0.1 volts. I'm just assuming things. And this current direction is like this. And this is 10 microamps of current. So how can I write the polarities of the voltage now? So this voltage polarity, initially this was plus minus. Now this will be plus minus. Right? This will be plus minus. So this will be plus and this will be minus. Now if I observe this carefully, that obviously this is plus minus, and inductor doesn't want to change this current, right? It will try to keep this 10 ampere flowing. Okay, and if the 10 amperes flows, what is happening? This 10 amperes is flowing in the positive terminal, and you know about power, if the current is flowing into the positive terminal, it absorbs power. So this time, right, what is happening? Inductor, previously what was happening, if you observe carefully, previously what was happening, that some current was flowing just before, let's say just before pi minus, right? At pi minus, what will happen? At pi minus, let's assume also it's almost around 9.9 microamperes of current, 9.9 microamperes of current. And if you put sine of 3.14, 3.1, something like that, it will be almost equals to 0.1, but something positive. It will be very small value, but it will be something positive. So I can write my positive value as this. Okay, and the inductor current is this, right? It is in this direction, which is 9.9 micro, somewhat lower, okay, but still 9.9 micro. Now if you observe that here, right, current is leaving the positive terminal. So from 0 to pi, right, omega t equals to 0 to pi, my inductor, like the power is flowing from the source to load. Okay, source to load. Hence, inductor is charging. Inductor is energizing. Inductor is energizing. But at this moment, what is happening? At pi plus, what is happening? At pi plus, this is negative and current is flowing into it. So, inductor is providing energy to both. Like this resistor is always dissipates energy, right? Source can absorb and deliver energy, but resistor always dissipates. So inductor gives energy to both the resistor and the source. Okay, so this time, right, the power is flowing from the source to load. Power is flowing from, not source to load, power is flowing from load to source. But if you observe carefully, inductor has to provide energy to both this resistor and capacitor. So it will dissipate much faster. And what will happen at steady state? What will happen is current will increase, decrease, current will increase, decrease. But at steady state, it will reach some value. What will that value? We'll discuss now. So that value will be basically this. Okay, this will be okay. Just hold on. That value will be Vm minus 0.7 by Z. Like I have drawn the current waveforms. If I see over here, just hold on. I must have drawn. So what is happening is, so it is discharging, and as I said, right, it will discharge much faster because it has to dissipate energy through this resistor as well. So let's assume it discharges at omega t equals to beta, some angle beta, right? It discharges because it has to discharge much faster because the amount that it has charged, right, it will discharge faster because it is dissipating through the resistor as well and through the source as well. Okay, that's why it will dissipate much faster. And I will prove you also it will dissipate faster. Okay, so here, right, one thing we observe is that, again, if you have studied transient, you will know AC transient, you will know we can write our current in terms of this and like this, right? This is 0.7 is due to this drop across this diode, and you have to watch AC transient to understand how this equation came from. Okay, then I can write everything here. One thing I have to notice is the time constant. Just hold on a second, I have to check one thing. Yeah, sorry, my storage was over in my phone, that's why I had to restart this. So here I was explaining, right? So this will be the current, and if I just compare the time constant, so if I just compare the time constant here, I will just compare the tau. So tau in this case, right, is what? L by R, and L is what? L is 10, if I see here, L is 10 nano Henry, 10 nano by 10 kilo. So this will be almost 1 picosecond, right? 1 picosecond. But our time period is still same. It is 1 microsecond. This time, right, our time period is much larger than the tau. So this time period is much larger. So the inductor will be able to reach steady state at much faster rate. So whenever we write this equation, right, this is my tau and this is my t. So my time window is much larger than this tau. So what will happen? E raised to power minus very large number. Okay, because t is very large and tau is very small. Very large number, e raised to power minus. So this will tend to 0. This will tend to 0. So this will go to 0. So we won't see any transient because our tau is very low than the time period. So transient will die off throughout the whole sine wave. So we will have this only steady state response. Okay, and in the steady state response, whatever we see is that it is somewhat of a sine. It is somewhat of a sine value. And how will it look? It will look something like this. That it will charge. Then it will reach some maximum value, and then again it will discharge. It will go to 0, and then again after some time it will again charge and discharge, like that. When would it reach to maximum value? If we see, right, it will reach to maximum value at omega t equals to pi. Why? Because just before omega t equals to pi, it was receiving energy, hence it was charging, it was energizing, hence the current was increasing because the VL was positive. Just after this, what will happen? Even though the supply is negative, the VL, now the inductor is supplying the supply source and the resistor. So it is supplying, obviously, like VL will be negative because it is supplying energy, hence the current will reduce because it is supplying, right? It cannot supply infinite energy, only this source can, but this cannot, right? This cannot. So the current will reduce, and at this point the current will be maximum. So I have assumed 10 micro, it can be anything. Okay, whatever the value, I will also say that. So at omega t equals to pi, it is attaining maximum value. So at omega t equals to pi, I am getting IO as IO maximum. And what is the value of the IO maximum? The value of the IO maximum is simply, if I put here omega t equals to pi, so it will be Vm minus 0.7, that is 4.3 by z, and z value I have told what is the z. Z is under root omega L square plus r square into sine pi minus phi. Phi also I have told tan inverse omega L by r. Okay, so if you compute this value, right, this will be your IO max. Okay, I've told you everything, and just compute, put the value of z and pi, you can get the value. After that, current will reduce because inductor is supplying energy to the source and the resistor. Current will reduce, and current will reduce in this format only. Okay, and to what value will it reduce? So I have assumed at omega t equals to beta. Beta is also known as the extension angle where the current becomes 0. It will be 0. So my current will be 0 here. IO will be 0. So I will simply replace IO with 0 in this equation. I'll simply replace IO with 0 in this equation. So if I replace IO with 0, right, this will be sine of beta minus phi. So two things can happen. My beta, right, beta cannot obviously be more than 2 pi, and it has to be more than pi obviously, because at pi I have assumed that it is getting maximum current, so obviously it can go to 0. Okay, beta has to be between this range. So obviously beta minus phi equals to 0 goes out of the picture, because phi can never be greater than pi by 2. Phi has to be less than pi by 2, right? That is one basic thing that we know about AC circuits. So for AC, passive AC circuits, so what will happen is that I will equate this with pi. If I equate this with pi, my beta will come out to be pi plus phi. So at pi plus phi, it will totally discharge. And how much time for it is charging? It is charging from phi, from 0.7, that is alpha, to pi. And normally what will happen? Alpha is much lower value than this beta, right? So than this phi as well. So the duration is much larger for charging than discharging. So like what will happen? Up until this place, nothing will happen because diode will be off. I will just draw. Diode will be off. Then at alpha, the value will be 0.7 of the supply, and diode will just turn on. And as the diode turns on, what will happen is inductor will start to charge, hence the current will increase, and it will increase up until this point at pi. Just after pi, right, the source voltage is negative. If the source voltage is negative, inductor has to supply the energy, hence the current will start decreasing, and it will start like decreasing very fast manner. It will decrease to here at this point at the angle beta, and after beta, at the angle beta, after beta, it will be simply off. There will be no charge flow, and our V will be simply Vs at that point of time. Okay, so here what will happen is the graphs will be something like this. At alpha, the current graph, from the current graph you will understand. At alpha, current is 0, and after that current is increasing. Then it reaches IO max. IO max is this value. After that, what will happen? Source is negative, hence inductor has to supply the current, so it will reduce up until beta, and then current will be 0 and it will remain 0 because inductor wants to stay at steady state. Again at 2 pi plus alpha, that is at 0.7, again it will turn on and inductor will charge. So what will be the VL? VL will be simply this, right? VL will be simply this, and the diode voltage, right? Diode voltage will be simply this. Okay, why? If you understand VL, what is happening here? VL is positive because here the diode just turned on. And what will happen? The current still is 0, right? Current still is 0 across the inductor because it here if you see where is it? Here, right? Not here, just here. So voltage across the inductor was 0. Diode just turned on. If the diode just turned on, current is still 0. So what will be the voltage across this? The voltage across this just after this, right? This voltage will increase to some value, and it will try to reach that increase, right, to make the current 0. Okay, to make the current 0. So our VL, right, I have made a mistake here. I think that it won't be because current is 0 here. If the current is 0, this Vs directly comes across this, so this is 0.7. So VL will be still 0. Okay, so this won't be 0.7 here. This will be some other value, right? Because VL can change to some other value, and this will be some other value. Okay, this won't be 0.7. This will be some other value. Okay, this will be some value. Let's say V X. Okay, because I don't know what value it will go to. And after that, what will happen is that this will, because this starts from 0, right? So I think this will also start from 0 itself. Sorry for that. My like throat is a bit bad, and like I'm really tired. I have to do a lot of work, and if some calculation mistakes happen here, right, I'm sorry because this is like night of 2:30 a.m. right now, and I'm recording this. So and I have to get this video out by tomorrow, so that's why I'm doing all this. So my throat is also a bit bad now, right? So this will start from alpha, and this will increase. This will be some non-linear function. Okay, so I cannot directly plot V at steady state. I can, but not at steady state as well, because plotting V will be difficult here. Like you have to differentiate this function. And that will be my VL simply, because IO of t is this, and if you differentiate, you will get your VL of t. So your VL of t will be something like this, but you go through the current waveform only. And diode, I hope you understand, because after this alpha, right, reaches 0.7 and diode turns on. If the diode remains on, the VD will be simply 0.7 volts only. But after this, right, beta angle, what will happen? Diode will turn off, and as soon as the diode turns off, the potential at this node will be simply Vs, because no current flows through this, and potential here will be 0 because VL indicator has reached steady state, so it will be simply 0. So hence the potential of this diode will be simply equals to plus Vs. So it will be simply negative. It has to block the reverse voltage, and it will go on. So our V, right, whatever they asked us to plot, is V equals to VL plus VD, or you can simplify this. This will be equals to L di dt plus VD. Okay, so you differentiate this current, okay, then you add, and then you will be able to find your voltage. Okay, so if there is some mistake, you do let me know in the comments. This was the solution that I tried to came up with. Okay, this was a very, very good question, and you definitely should try this question. I will give you as homework. This is a simple question of op-amp diodes. Like this is the last question of diode circuits. Okay, and next lecture I will solve capacitors. Okay, I am giving you a few homework questions for capacitors. This is the RAM response, so this can also be asked in interviews. So if you want this, you have to obviously like the video and like share on LinkedIn, like the LinkedIn post that I post regularly about questions, so you can go and like that. So these are a few questions that I will solve in the next video of capacitors, so you can see all this, right? And also I have uploaded a video of switch capacitors in our main channel Perfusion. You can go and check out that video. That is also a very, very important question for lecture for gate as well as placement students. Thank you for watching, and I will see you in the next video.